Log on, tune in, find out. Another good idea from Cambridge.
Homogenization methods for metamaterials.
Thank you, Slava. Thanks to the organizers. Great pleasure to be here again in Cambridge. Somewhat nostalgic. I did my postdoc here a long time ago. Today I will try to give a little introduction and a sort of critical review on use of.
People then say it's all wrong, right?
Sorry?
Give counterexample. You first prove it, then give a counterexample.
Exactly. Right. Homogenization methods for metamaterials. So metamaterials is a buzzy word these days. For about a decade or so, this all comes from physicists who basically argue that one can invent certain materials called metamaterials with highly unusual physical properties. So my aim here is to try to understand what it means in mathematical language, and then if and how math can help both in subjecting the ideas based on physical intuition to scrutiny of rigorous mathematical analysis and seeing what may be right but what could be wrong, but also perhaps to discover some interesting effects on the way of doing so. That's the motivation. Here is the question: what are metamaterials? There could be several possible answers. One of them is, as I said, materials with highly unusual properties, and those properties are achieved by composition, right? Heterogeneous materials, composites, which display this sort of properties. So the physical context, the original motivation comes from electromagnetics. So you have to deal with Maxwell's equations, and basically we can think about a heterogeneous electromagnetic medium described by two parameters, right? Electric permittivity epsilon and magnetic permeability mu, right? There could be some sources here, current and density. This is a classical setup, or we could think acoustic or elastic metamaterials, and all those effects are intrinsically dynamic effects. We need to talk about acoustics or elastodynamics. And here the parameters would be density, and in the context of elastodynamics, and elasticity tensor. Okay. So far so good. So all nature-made materials, they are usual in a sense that the constitutive parameters epsilon, mu, rho, and c are usually positive. Tensors could have some imaginary parts as well to account for absorption. So mathematically, there is no a priori reason why some of them could not have a negative real part, and this is a question which is of big interest to physicists apparently. So I'm a learner just trying to learn. Can any of this be made negative via some kind of homogenization? Why bother? Good question. So if any of those could suddenly become negative, then this opens up way to whole bunch of interesting effects. There is incomplete list here: negative refraction, super resolution. So some ideas of this kind originally come from Veselago in the 60s, long time ago. And then Pendry and co-workers actively are pursuing this agenda over the last decade or so. There are other effects, so-called anomalous localized resonance, and cloaking is another buzzword, right? External cloaking due to Milton and co-workers. So I fetched a paper of Pendry. So basically, his argument is simple. Hope everyone can see what is here. So he's saying that what is epsilon and mu, right? Properties of electrodynamic medium, which are a result of averaging the effect of micromolecules and so on, right? There could be effects of polarization and magnetization, right? Due to some kind of arrangements of atoms and orbiting electrons. So basically, the idea is that why couldn't we enhance or alter this sort of effects by introducing artificially various inclusions, specially designed. One of them is displayed here. Split ring resonators, they're called, so that those the visible macroscopic properties could become unusual, for example, negative. So, and one phenomenon is negative refraction. Basically, my naive understanding of that is, suppose there is a conventional kind of electrodynamic medium, epsilon and mu, both positive, could be vacuum here, and take a slab, a lens, and suppose we are clever, we manage somehow to achieve epsilon and mu both negative. What would that imply? -1, right, sorry, -1. Yeah, I do apologize. What would that imply? So if I have a source somewhere to the left, then if I forget for a moment about the other boundary, this is a classical half-space problem, and there is a phenomenon of refraction. Usually the wave would refract here, but here we have a negative refraction, and the angle, if you believe it for a moment, the angle would just go there, and then again, and return somewhere on the original axis. And of course, for this case, it doesn't matter how we do it, it will always go like this, and then there will be perfect focusing. So he proclaimed that negative refraction makes perfect lenses. Then a mathematician will ask a question: what is the formulation of the problem? Right? That's a good question. So PDE, Maxwell PDE system, and a source, a delta function or something on the right-hand side. And of course, if you have a perfect focusing, there is another delta function on the right, but it is the solution. So there is a source here and no source is there, right? There is an element of suspicion. Yeah. So, and Milton examined this a little bit more systematically, mathematically. That's my understanding. People will correct me if I believe that's simplified. If one allows for a little absorption in this medium, then the whole picture falls apart. So basically, a mathematician would say that there is a problem with the limited absorption principle. When delta goes to 0, the solution doesn't quite stabilize to perfect focusing, and instead it displays some kind of delta is infinitely small, and there are some wild oscillations generated somewhere which don't disappear in the limit. And Milton has called it anomalous localized resonance. And that's not what I'm going to talk about. So basically, here you can, in some simplified setting, you could say that it's not that bad for Pendry. Actually, it's kind of politically correct way of saying this. That the effect of super resolution does hold, but in some approximation with some disclaimers and with some limitations. And those so maths advocation for maths, right? It allows to establish some limitations of the ideas based on physical intuition. But in the course of doing so, Milton has also discovered the effect of external clocking, that well, I won't go to the details for one reason I don't fully understand them myself. So, but essentially, what happens here is that the source has to be quite close to this lens in this case, and in a sense, instead of kind of focusing, the two cancel each other, and if you are some outside observer, you could see neither, right, nor the source, nor the image, right? The source is cloaked, and this is an alternative mechanism for cloaking. The other alternative is due to transformation optics, which is actively explored now. Slava Korolev, who is here, is one of kind of front runners, right, in developing mathematical theories for this. It's not what I will be going to talk about. So basically, the question is, and there is already a bit of skepticism, right? Now, what we can achieve via what we can and what we couldn't achieve via homogenization, right? And this is really a setting for homogenization if you look at Pendry's paper. Okay. And that's my answer, right? Well, sometimes in some sense. So, if you want to inject some funny objects inside, stir them up, this is the setting for homogenization. And here is a recap of classical homogenization. So we think about a medium with highly heterogeneous properties. So in the simplest case, we can imagine periodically dispersed inclusions in a matrix, and there are two materials with two different properties. And of course, the intuition suggests that when the parameter epsilon of heterogeneity becomes small, we perceive the whole thing as a homogeneous medium with effective macroscopic, homogenized, whatever is your favorite word, properties which are related in some way to properties of both components, but also to the composition, microgeometry of mixing. Okay, and to make life easier, we can take the same equation which describes both antiplane shear elastodynamics or TM electrodynamics. Mathematically, they are equivalent, so it is either let me just get more here. So either the density or mu magnetic permittivity. So A is elastic stiffness or inverse of the electric permittivity. So a key assumption in classical homogenization is that original things we take, they both have to be uniformly positive. Not only are not allowed to become negative, even not allowed to come too close to zero, uniformly positive and uniformly bounded. So then, the standard recipe of doing two-scale asymptotic expansions. So a priori we seek a solution to my initial boundary value problem, in this case in a two-scale form with respect to small parameter epsilon, and the unknowns are functions which vary both on macroscopic scale x and on microscopic scale y. Okay, and then you plug these ansatz into your equation and start formally equating the coefficients with equal powers. Then you can prove all the theorems in the end. And the first observation you make is that the main order term doesn't. So if I had technical facility, I would have taken a big red marker and crossed out the x over epsilon term, right? There is no dependence on fast variable. And then you make two more steps. I'll just uncover it all. Equating next order coefficients leads to the so-called corrector problem. So you need to find microscopic variation in terms of gradient of macroscopic field. So what is called the cell problem. And a third and final step, you end up with a homogenized equation, which is of the same type as the original equation, except it is not heterogeneous, and the homogenized coefficients. Density is simply the volume average of the original density, right? The angle brackets denote averaging with respect to the periodicity cell, and slightly more cunning expression for the homogenized tensor. We call it stiffness or electric permittivity inverse. In terms of solutions of this problem, well, what is important is that in the course of doing so, the condition of uniform positivity and boundedness is inherited by homogenization, which is not a good news for metamaterials, right? So but it's also means that we have to do something slightly more clever than classical homogenization to get around this. And for those who care, this all can be done.
What do you need to say about the initial conditions of forcing term f of, was it f of x and t? I see it's f of x in that red equation.
I think it is, didn't I say it here? So the initial condition, right, the right-hand side f, so I assume that there is beginning of times, right, that everything was still before some time, and then it started shaking, right, and then if you can also...
And it doesn't have to be smooth, it doesn't have to be bounded or anything at all.
Well, f 0 t h minus 1, would that make you happy? So generally speaking, it could be rather nasty object, right?
Could be a nasty function of time.
Could be a nasty function of x, right?
And the fact that it
but it is...
And the fact that it generates wavelengths
right.
and epsilon doesn't matter to you at all.
Right. Sorry, what say it again?
If that f of x and t had something like a delta function in it, just to speak colloquially, it would
Right.
have all wavelengths, including arbitrarily short.
Right.
But you're still saying that this prescription works.
You see what is hidden here, that I disallow short wavelengths, right? In the course of doing this. Right. Everything is nice and
So what do you
smooth,
mean
right?
by this?
I don't
Okay.
allow for...
Yeah, so it's a C0.
Right.
What's a T to H? Well, is that what you meant?
Right.
Oh, it's there now. Did you write that all the time?
So we can assume everything is nice and smooth and so on. There are ways to relax various assumptions here, right? So do we have a duster? I'm not sure we do. Anyway, have to take room. That's pretty good. Right. Okay then. Just returning where I stopped. Okay. Fine. So that's no good. And a way to, if you look at what the way physicists argue and translate it into mathematical language, you will realize that this sort of problems have been studied for quite a while. So basically physicists are saying that we want to propagate some long wave in the matrix, but we want to inject into it what they call microresonances. So such funny objects for which the associated frequency would be close to the resonant frequency of the inclusion. So if you translate it to asymptotic language, you will realize that you want a high contrast in the properties of the matrix and of the inclusion. This means that you want to propagate waves in such a frequency range so that in the matrix, outside your inclusions, those would be long waves, but in the inclusion they would be over resonance. Wave frequencies mean the wavelength in the inclusion is of the order of the size of the inclusion. And if you play with dimensional analysis, you can say, okay, let there be a high contrast. Inclusions are much softer than the matrix. I talk about elastic context. So there is a parameter delta, and as often in life, we have two small parameters, delta and epsilon, and everything depends on how one is scaled against the other. And this dimensional analysis basically said that there is only one critical scaling, delta of order epsilon squared. And you can argue in different ways why critical, so there's physical argument here, or if you prefer asymptotic expansions approach. This is exactly, you remember I was crossed out in a classical homogenization, I crossed out x over epsilon term, was my first step. Here there is no reason why I should do this anymore, since there is a degeneracy, and it is order epsilon squared degeneracy, which exactly balances the possibility of retaining oscillations. Again, physically means that there is slow variation of the field outside and fast variation in the inclusion, right? And then we aspire for ending up with a system of, we can still call it homogenized, but it is homogenized in inverted commas, equations for U naught, which retains dependence on the fast variable. Okay, where is it? Didn't I have a funny picture to this effect? Right, I drawn it here anyway. So, two-scale asymptotic expansion, right? And then, one page disappeared, right? Right. Yeah, so basically, so I need to explain it here. The main order term, right, U epsilon is a function of x and x over epsilon, right? It could be t dependence. Now I'm talking about spectral problem with a fixed frequency. Now, this is still a function of x only, right, in the matrix, and it is convenient to split it into two pieces, function of x and some extra bit which is allowed to vary microscopically in the inclusion. So, and we hope to end up with a coupled, right, a coupled system for U naught comma V. Right? You remember in classical homogenization we had just homogenized equation for U naught only. Now we have a coupled system which for some funny reason disappeared from my slide in the course
It's
of...
too small, epsilon's too small.
Sorry?
Epsilon's too small, you can see.
Well, here you see epsilon is originally small parameter, but your unknown is a function of x and y, which is deemed as an independent variable, right? After you turn your handle, you end up with a system of equations for functions of u and y, right? So you have u of x and x, v of x and y, right? No epsilon anymore, right? But that is the result of honestly passing to the limit in epsilon, and essentially that's, I have to redisplay it since it disappeared. So minus div a hom grad u naught equals lambda is my spectral parameter, right? The density was taken 1 in this case, u naught. So this is a classical case, right? For so lambda is a frequency squared, right? Helmholtz equation essentially for wave propagation. Here it is coupled, u naught plus v, right? And angle brackets is averaging in a fast variable. And then there is a similar system for the simplest case of the Laplace v. So this is all in x, right? And this is in y. This is a straightforward outcome of turning the handle in a similar way, but accounting for this new effect of coupling, right? And the whole point is that when you uncouple this now to scale limit system, you really can account for some of those effects of micro resonances. Now,
Excuse me.
yes.
What's AH here? The homogenized coefficient. How do you compute
So
that?
AH is a homogenized coefficient for perforated domain if you just throw away the inclusions and replace them by voids, right? Zeros. Yes, and this is essentially formally it is also the general problem, but essentially that's classical homogenization, right? You have to do it in a slightly more clever way, but that's all fine and has all the properties of uniform positivity and so on, right? So now you want to uncouple bottom up, right? Take the lower equation, pretend you know U0. U0 is a function of x only. You can take it out here, right? U0 should have been here. And b is a function of y only. Essentially, you have to, there will be a constant on the right-hand side, and you have to take the composition of unity, and you can make a spectral representation.
So B is V, right? B is V.
What?
B is no.
So-
B is just functional. Yeah, right.
Yeah, just a way to take the constant out. X and y are deemed independent. Lambda U0 is a constant. Take it out. B is a function that retains 1 on the right-hand side, and I think yeah, I have here. There should be minus.
Just one.
There should be minus lambda here, right?
Lambda there,
Yes.
Lambda mission, yes.
Yeah, minus
Lambda
b
mission, yes. That's
minus lambda b equals 1, right? Lambda b is
And in this case, when we choose A0 is just 1. Correct? What is A0 in this case?
so a0 is some positive.
Remember,
Sorry, a home, right? Too many typos. A0 is a.
clear, and A0 in the,
Sorry.
in the model which you have chosen was
Right.
It was
Right. A0 is 1. Yeah, you're right. You're right. Yes. A home is an x. A0 is Laplace possibility. Right? Possibility. So, and then you take a spectral decomposition, right? If you have eigenfunctions and eigenvalues for the Dirichlet Laplacian in a single isolated inclusion, right? This is an extra thing you put on the top of a function you know that has to satisfy zero Dirichlet boundary conditions in the boundary. So that's straightforward calculation, and then you plug it here and take the average, and you will end up with a mysterious equation which looks slightly more encouraging for metamaterial people, since you eliminate V and you end up with equation for U0 only, and because of this cunning trick, lambda is replaced by a mysterious function beta of lambda, right, which is what it is, right? This is a result of spectral decomposition. You should avoid eigenfunctions, right? The problem would not be solvable. Not surprisingly, this function beta blows up, lambda 1, lambda 2, and so on, at eigenvalues for the isolated inclusion problem. And otherwise, it is easy to see it sort of monotonically increasing between the eigenfunctions and blows up to infinity. And this is similar to pictures which physicists draw. Sorry?
Red pieces is where beta
Yes, red pieces is where beta is negative, and this is of some special interest, right, apparently. So, and that is too clever for myself to invent. So that was done by Zhikov in the year 2000 with no knowledge or relation to metamaterials. He was just, yes.
Where did the time go?
The time was eliminated. I took time harmonic case, right? I took a frequency omega, right? So lambda.
Omega is
So lambda is rho omega squared, right? And I took density rho constant for simplicity.
You mentioned all that and I didn't even hear it, is that right?
Did I? Yeah, but somewhere. Yeah, I suspect one of my slides disappeared mysteriously. Should have been there. All right, okay, so that's a formal calculation, still not purely convincing mathematically, but if you believe it, then you are inclined to interpret it as you achieved for a range of frequencies, you have achieved negative value of the parameter, which looks like a substitute for density as it stood there, right? Or a magnetic permittivity if you are in the context of electromagnetics. So,
Sorry, so is what you're aiming for is that the solution when you look on a larger length scale, so when you average over y,
right.
it's got the desired property. Is that
Yeah, so basically, as I said, the honest solution remains two scale, right? But it is two scale only in the inclusion and remains function of x only in the matrix. So if you eliminate, uncouple the system, to try to end up with equation for u naught only, as a result of the uncoupling, you end up with this mysterious equation for u naught, right, which contains beta of lambda is the outcome of the process of uncoupling. And straight after the eigenfunctions, beta dives to minus infinity and then remains negative, right, up to the moment where it crosses the point. Right?
what I mean now is that the effect that they want to observe physically is on the length scale of x, so you can, in that sense, ignore the y variation.
Yes, you can say like this. Yes, so that is a macroscopic effect, right? Okay. So, and for those who care, this can be all done rigorously, and the language for this, so I will be brief, it is a language of two-scale convergence, and essentially you have to make sense of the fact that your function of x only behaves when epsilon small is a function of two variables x and x over epsilon, right, retaining the oscillations, right? And what is the meaning of this mysterious funny wiggle? So you can put an arrow here and say that this function of two variables is properly understood limit of the function of one variable as x goes to 0, but this is what we call a two-scale limit. It's again, and here you can repeat all functional analysis starting from weak convergence and then strong convergence. You can make sense of weak to scale convergence, where essentially those now weak convergence, you take a test function, but you now take an oscillatory test function, right? And this has a meaning that you test not only the mean about which it oscillates, but the pattern of the wiggles, right? And this is all well understood, and then a strong convergence is a result of duality. You take all already defined weakly convergence sequences as the test functions, and in fact, the technical language, when you have enough regularity, it ensures the convergence of norms, right? That if you have strong convergence of those two, essentially this means that the difference between the two is small in the limit when in L2 norm, in fact. Right, and as soon as you define this funny, what is called two-scale convergence, then you connect the two walls, right? The functions of a single variable and the functions of two variables, and you can restate all whatever is your favorite language. You can talk about spectral two-scale convergence, for example, that the original underlying operator, it is another spectral people here, this self-adjoint operator in L2 of omega, and it converges in the sense of two-scale operator convergence to another operator which is self-adjoint in the bigger space, right, in the space of functions of x and y, right? There is two-scale resolved convergence. I believe this is rigorous definition of due to Zhikov. Just, I guess that may be a bit of technicality, but I guess it is important to state that there is a technical language for making rigorous sense of all these formal calculations. Since you are on the risky side when you recover these counterintuitive effects, right, of negative fractions. So it seems that in this case, at least, you can make sense of this, and not only by a formal asymptotic calculation, by rigorous analysis, error bounds, and so on, right? So what is the outcome is that essentially in the language of spectral theory, this funny red bands, gaps they are, in fact, red segments where beta is positive are band gaps in the Floquet-Bloch spectrum of the operator. So there are band gaps in the spectrum surviving to the very limit when epsilon becomes infinitely small, and physically this means that frequencies within the gap range are not allowed to propagate, right? The resonances don't let them propagate in wave state localized, right? And beta is negative. So Zhikov didn't care about physics. Bouchette and Fellbach rediscovered this all and additionally interpreted this in terms of negative magnetism. And now it goes further for elastodynamics negative density. So interesting thing about this is beta could be negative or positive. If it is negative, then waves couldn't propagate, right? Have localization. If they are positive, waves propagate, but there is still a highly nonlinear dependence on frequency, right? On spectral parameter, which is a source of dispersion, right? And you can achieve very high dispersion, also other funny effects like group velocity, very different from phase velocity, and so it has some interesting interpretation in terms of coupled resonances. I'm not talking about here right now. Okay, I think what is the moral so far? So essentially, the moral is that this physical intuition based on effect of microresonances could be supported in the context of continuum mechanics by allowing high contrast in the properties and working in the appropriate range, right? And it's indeed, you can see by naked eye the effect of the microresonances, right? Something special happens when you are close to the eigenfrequencies of the inclusion, right? And macroscopic wave either stops propagating or develops high dispersion. You remember beta looks like tan function. Okay, so and you remember there were, you can interpret it as a negative rho, right, or negative mu. So in the context of electromagnetics, there is always two things here, epsilon, mu, and here you have A or C, elasticity tensor or conductivity, and here you have rho, right? In fact, this is epsilon inverse, right? To make association with that. So in some sense, that could be made negative. How about this thing? That's a bit less clear, but there is a funny duality here. Since originally we had time-dependent equations, right? And we have made Fourier transform. John caught me, right? I didn't explain it properly. From time to frequency, and then we end up with this effective behavior, which is a two-scale and which displays for the slow variable. It displays in one way or other beta of lambda, right? You can write it beta of omega, highly nonlinear dependence on frequency. So I could have done from the very beginning, I could have done elimination in the time-dependent equations, working in time domain rather than in frequency domain. Or I could, in the end, do back Fourier or Laplace transform here. And the fact that I have this dispersive term, nonlinear dependence on the spectral parameter, means that I will have a memory effect, right? There will be non-local term in homogenization, but it will be spatial, temporary non-locality, right? temporal non-locality upon Fourier transform translates into nonlinear dependence on the spectral parameter, right? Then you can ask, in fact, some time ago, right here in Newton Institute, Zhikov was visiting and we chatted about it. At that someone asked a question that was well understood that time non-locality by homogenization. Can you achieve instead a spatial non-locality by homogenization? He said, why not? What is the difference? What is time? There is nothing special about time. You just draw one more variable, right? Why don't you take this picture when you had epsilon squared on a cross section and two-dimensional, let it be as it was on my blackboard, and add one more variable, right? x3, call it. And try doing with x3 the same thing as you did with time, and then you do a simple calculation, and then you observe that indeed you will end up with effective relations which are now spatially non-local, right? And then if you play it back and forth via Fourier transform, so spatial non-locality kind of, would that help? It's kind of a philosophical view, right? You beta, so omega, so is Fourier dual of time, right? So beta of omega, nonlinear dispersive, T non-local. This means that X non-local, by analogy, X non-local should translate to beta or whatever, in fact, possibly this A thing, depend what is the substitute for frequency of wave number, right?
Okay.
There could be nonlinear dependence, and there could be gaps, you can say, not in frequencies, but in the wave numbers, directional gaps, right? So mathematically, I guess I start feeling why Slava is going to general relativity, right? There's something at some stage it is difficult to distinguish between X and T. They are coupled in such a way that you don't really know which is, and John also knows something possibly related. So in one way or other, it appears that there is no reason why you couldn't extend this sort of calculations to recover not only frequency-dependent sign change and gaps, but also k-dependent, direction-dependent sign change and gaps. If you look carefully at what's happening here, you have to, originally you start from this understood, you do have to have a high contrast, right? On a cross-section you have high contrast, you add one more variable, and there you need to keep your parameter of order 1, right? And as a result of this, you end up with a pre-homogenized system which is degenerate, right? Which has one term of order 1 and the other of order epsilon squared, but it is partially degenerate. Some components degenerate, others remain stiff, right? So, and this gives rise to some more effects, essentially. So, and this is what we observed. We have joint paper with Zhikov, Kirill Chernychenko, now in Cardiff, then my PhD student a long time ago. So essentially, without going to the details, you recover this sort of effects here, and you need to deal with some more general degeneracy, right? Partial degeneracy to understand it all. Here is an attempt to give summary so far. So the hope is to achieve some or all parameters, negativity of some or all parameters. Okay. So we can achieve negativity of beta, but for restricted range of frequencies, and even if we achieve it, there is a dispersion in, so that the dependence on omega varies, right? So we have to be careful about this thing. So formally, we could achieve some sort of negativity for A as well, right? Partially, in a sense, but you can call it spatial dispersion, right? It will kind of be sensitive to the direction, since spatially non-local. So, in general, you have again, you have a non-local operator, right? But if you allow yourself to do really Fourier transforms in time and in space, it all localizes, but it will retain dependence on either or both of the spectral parameters, and for some ranges of the two, it may suddenly change sign. And John is here, John Willis, hiding. So in fact, much of this was directly and indirectly motivated by my interactions with John over the years, who John is not quite a homogenization guy, yeah, that's the right summary, but in his own way he understands these things better than me. Basically, a long time ago, John argued that outside homogenization, non-locality is a general feature of ensemble averaging of for the composites, right? So essentially, if you take an ensemble of them and average no epsilon tending to 0, you will retain non-locality. So here, it's, I guess, interpretation is that before I start sending my epsilon to 0, I will have John-like non-locality, but then in classical homogenization it disappears in the limit, and in this non-classical case it sort of stays up to the very limit but retains some slightly more explicit two-scale structure, right, which you can exploit sometimes. And in fact, I think this is an issue John bumped, I mentioned already before, that, and I think there is a similar issue in the context of two-scale homogenization. At some stage, you have difficulty in interpreting which part is sort of stiffness, which is a density, which is epsilon, which is mu, right? So there is some non-uniqueness in defining those non-local entities, right? At some stage you may deal them and allow for this non-uniqueness and live with this. In fact, this paper of Bouchetté and Borel, it deals, so I need to just looked at it yesterday in some more detail. So basically, if you allow these fibers, you remember, high contrast fibers, right? You get some spatially dependent non-locality and some spatial localization here. But what they did what they call reiterated homogenization. Took those fibers but then cut them through and make the little box, homogenized it in some way, and then inserted it into the other periodicity cell, right? And in this way they claim they could achieve local negative, partially negative A, right, or epsilon in the electromagnetic context. They're saying local negative epsilon effective is a big awkward problem in homogenization for Maxwell. Two meanings of epsilon, right? That's absolute nightmare, right? So LITEC has two different ways of writing. So epsilon is for electric permittivity, right? Via reiterated homogenization, two-step, right? They somehow place the magic. You can achieve negativity of some component, and if you do it one more time, then you can make both of them negative. Now, there is also, this is an introduction and a review, right? The other look, how I understand it, that if you want to do these things for Maxwell, of course, we would say just take high contrast in electromagnetic properties. For example, in epsilon, mu is physically hardly different magnetic materials, right? For natural magnetic materials, mu is nearly always about 1. For epsilon, you can make some small range variables. No way you can achieve you can take original materials with high contrast. So people, again following some physical ideas of Pendry, one could, and how I understand them, is to develop some micro-resonance type effect, not due to the high contrast, but due to special geometry. And this is the idea behind the split ring resonator, right? Where you have nearly closed annulus and a little, so basically if this is of order epsilon, and there is a gap of order epsilon cube, right? And this is different from this epsilon, which is electric permittivity. And simultaneously, well, we are less sure about permittivities, but conductivity could really be made very high, right? And then if you allow for a very high conductivity here, sigma is of order epsilon to some power minus alpha, you can work out what alpha is, then you will end up with this geometrically designed resonances can play with the parameters, and again you will be in the regime of low frequency propagation in the matrix. It will be close to sort of current will want to go back and forth along this thick, and there is a capacity type effect here. I think this is a continuum version of inductor capacitor resonance, right? Those who did, I just done L levels with my physics L levels with my son, right? So CL, right? There is inductor capacitor resonance has some eigenfrequencies, and there you can play with the parameters, and here in the continuum version recover them. And this will have effect of negative mu exactly in the way the message is, I guess, that you don't need to seek in nature materials with high permittivity, since you will fail, but you can do something more clever, but essentially to the same effect. And then Milton said, you just give me those two materials, material A, which has at least some components of electric permittivity negative, and material B, which also has a negative component in magnetic permeability. Then Milton is saying I can do sequential lamination, mix them up in some intricate way. So essentially, this is a tool in the mechanics of components, right? If you have material A and material B, then you mix it up in certain direction, and then if the scaling of mixing is small, that in the end you will end up with material C, and then you can mix it up in the other direction, and then you can repeat it many or possibly infinitely many times, and sort of approximately realize quite sort of many configurations. And here you could approximately achieve any mixture. Okay, I think time is running up. Just okay, what do I need to say? Then basically, if you want, the emergent message is that on one hand, you need to play with high contrast and allow adjust classical homogenization for high contrast and for living with limit behaviors which remain to scale. And second message is that you really need to allow some partial degeneracies, not necessarily stiff matrix and soft inclusion, right? So some components of matrix could be soft in inclusion, stiff the other way around. At some stage you may not distinguish between inclusions and matrix. Just to flash it in you, kind of there are more interesting physical problems where you have this partial degeneracies, partial high contrast. The one is easy to imagine. Our current PhD student with Ilya Komotsky, Shane Cooper, has done work, also natural physically, when you have an elastic inclusion which is embedded in a stiff matrix, and its bulk modulus is stiff, but shear modulus is soft, right? It's kind of hard to compress, but easy to shear, right? And there also cells, you can pass to the limit. There are some additional effects. So essentially, there are only eigenfrequencies. You need to deal with the Stokes problem here and the incompressible limit. Some curious example of partially high contrast emerges in wave propagation along photonic crystal fibers. When you deal with full Maxwell and there is no high contrast, there could be just a moderate contrast between inclusions in the matrix, but there is additional parameter, so-called propagation constant, right? You have the axis of the waveguide and you have this k is a wave number of propagation, and there is a critical value. If k is close to certain critical value, then there is some kind of apparent high contrast develops. Since it deals with Maxwell, there are various degeneracies there, and again in the limit you have some matrix doesn't look as a fully stiff, right? It is not a function of x only, so it is allowed to depend on y, but in some funny way described by Cauchy-Riemann equation. So the dependency of this pair, normally you have to isolate electric and magnetic field components along the axis, and they may vary in y, but their combination is an analytic function, so Cauchy-Riemann conditions, and then you have to deal with technical issues and recover new effects. And here time is up. I suppose the organizer have instructed me to watch my own time, right, and to stop myself at right moment. Just finally to say that we are currently with Ilya Komotsky, we have a pretty thorough general understanding of I mean what you can imagine in the most general setting. You really expect that something happens when some components are of this critical scaling epsilon squared, but others are of order 1, right? And at some stage you don't really need to distinguish matrix and inclusion, isolated or not, or even some parts may be degenerate, other are not. And there is precise technical language here where you can see that the main order term, right, the order 1 component is not uniformly positive anymore. It could degenerate, but this higher other bit will correct it, and you can develop it for the systems. So there are some technicalities shaded with this. You don't need algebraic positivity of the tensors, but some differential sense positivity. And then essentially you can develop general theory, and what I omitted here completely, right? You have to carefully pass to the limit in the weak formulation of the original equation, taking two-scale test functions and using the language of two-scale convergence, and then you honestly, in an honest way, so there are various estimates, and what happens that in the end your two-scale limit will live in some funny space V, which is this microscopic oscillations which are not allowed by the degeneracy, right? In classical homogenization only constants are allowed, right? In this fully contrast case, constants here and arbitrary function there is still displayed. So generally there will be some close-up space of H1 which survives the action of this operator, right? And then you have to, there is some subtle duality which there is no way to discuss. You need to watch also fluxes, right? Duality between fields and fluxes and simultaneous, and how the two are connected in the limit. And there is a funny language here, and what essentially you need the only generic assumption or restriction you have to make. People know that you have to have Poincaré type inequalities, right, to control the oscillations and to establish compactness properties and so on. So basically here there is a generic assumption which holds. You check routinely, sometimes not entirely straightforward, starting from classical homogenization, fully degenerate case. So essentially there is a degeneracy and there is its orthogonal complement, you could say. So if you can decompose everything into two pieces, right, where things are fully degenerate, and in a supplement the non-degeneracy is reconstructed, then you are still in business and you can pass to the limit and justify all those formal constructions. Okay, and I think, isn't it the right time to summarize? It is indeed. I am my own chairman. Right, I think that's a little summary. Hope that the aim of today was to try to sort of deliver you this message that if you develop some non-classical version of homogenization which allows for high contrast, then you end up with 2-scale limits which can display a whole bunch of interesting effects, some of them consistent with physicists' expectations, but some raise some warnings and indicate at limitations of and over-optimism if you look more carefully at some physical predictions, right? So, but on the other hand, allows also hopefully not only to check what is right, what is wrong, but also gives rise to interesting new effects, right? Gives rise to more of such interesting effects, right? And I think, yeah, that's all there. It was periodic and linear, but in principle doesn't have to be. Chernyshenko, Cherdantsov developed recently some versions of some interesting new effects, and in that case, non-linear or variational problems. Doesn't have to be continuous, and so on. So I think that's all I wanted to say today. And if you ask me again, so what? So could those metamaterials be invented? The answer remains, well, in some sense, somehow. Possibly. Thank you.
Maybe questions?
In the degenerate case, it would be interesting to see what happens when you homogenize observables, energies.
Right.
Because the Bloch eigenvalue problem is probably very equal, I suppose.
Right. Yeah.
So I mean, like passing from the linear homogenization problem to the quadratically nonlinear one, and I think that all the world changes.
Yeah. Yeah. Another interesting observation that I believe on this way, by a formal calculation, you can recover Anderson localization, for example. However, I have no clue how to prove this. All other results, if you are in a linear, I guess you know what I mean, right? So far everything was periodic, and there was a single inclusion with a single set of eigenfrequencies, right? Therefore, you are either in the band or in the gap.
Right.
And you can prove, in either case, you can prove everything since you start with the Bloch wave spectral decomposition, and you argue that it survives passing to the limit, right? You have a limit to.
To make it a bit simpler and start by quasi-periodic or almost periodic or something.
Right.
Instead of going to the fully stochastic case.
Yeah, that's kind of
that
something to.
Might be manageable.
Yeah, that would be an interesting prospect. Yes.
I've heard material scientists talk about, I think it's
Martin-side.
Austinistic materials, that when you pull them that way, they get wider that way.
Negative Poisson ratio, it is called, yes.
So is that possible by homogenization?
And in fact, this is what I didn't mention, but that's exactly how the story goes. And basically, you can say this is the first example of metamaterial, or one of the first examples of metamaterials, long before Pendry, where you achieve unusual and somewhat counterintuitive methods. And if you look at a book of Milton, Milton Theory of Composites, he discusses the issue, and it's exactly, I think that he has even a picture to this effect. I'm a bit hesitant, there is some kind of simple intuition behind it, but you really invent, I won't dare about the precise detail, but you invent some periodic microstructure, and you can kind of intuitively see when you pull it, yes, there are some funny bits which push the neighbors aside, right, and by being pulled as a result of the composition.
And I've seen that in metal foams where they effectively have those levers.
Right.
But what I can't see is that could arise out of homogenization. In the sense that you're talking about, because these are a bunch of levers connected together. It's a lumped model. It's not. It's not a periodic structure with each one with a normal positive Poisson's ratio.
I thought that John may know better, don't you, John? My understanding is that Milton's example of negative Poisson ratio, essentially you can construct some periodic configuration to this effect, but with
Milton and also Rod Lakes, I guess.
right.
You know that name. I think Graham's first constructions were probably for things like you said, basically levers. But then you can sort of visualize filling in the gaps with some soft material of some kind, and you're almost there immediately, aren't you? So, and the homogenization business just means that the scale of the deformation that you're imposing runs over many, many periods. That's what it's saying. You know, you can either have wavelength like this, but the period epsilon becoming very small, or you can have a period like this and then the wavelength get very big. It's the same thing. So
I mean, it's
basically,
kind
if
of
you've done it with levers, you've done it. It's just Graham's made some pretty ones as well, you know,
right.
I guess.
And there are some nice pictures in that book, highly recommended. I think it is straight in the introduction, you know, the big book, Graham Milton Theory of Composites. In the introduction, there is a nice picture which I'm a bit hesitant to reproduce here, but of a periodic material with negative Poisson ratio, and then you can do it by homogenization.
Just a comment, I think when you move away from the periodic case, so place almost or stochastic, I think then you cannot even compute, I mean, then there will not be a corrector, most likely. So, I mean, the formal computation has to be sort of completely done on a different basis. Like if you think of what Raffaelli, Subanidis and people did.
Yeah. Papa Nicolau, Baradan and Kozlov, I think, studied independently stochastic homogenization in end of 70s, right? And they developed machinery, but there is the central issue that you have to understand corrector in a different way, and that is not, is it correct, it will be statistically homogeneous process. Some sort of technical problems with this.
Basically when you shift it, you have the same picture.
Yeah. Actually, there is, if you ask about this negative Poisson ratio, similar example of a negative thermal expansion, and it is easier to visualize, I think, Graham's. That when you have two materials, both have positive thermal expansion, but one is bigger than the other, and you make a funny construction, an essential building block of it is a pair, right, which you bond together along the long edge, and then of course when they expand, one expands more than the other, right, and it is bends more than expands, and the endpoints as a result get closer to each other, right, and then it is repeated macroscopically, and sort of another curious example, right, where you can achieve you hit thing and it shrinks as a result.
No more questions? That's it. Thank you very much.
Thank you.